3 seconds ago, at a hive bench somewhere in a morning apiary, a beekeeper pressed a hive tool into the propolis seal along the top edge of a brood box and pried the lid. Within 2 seconds, the colony had run a coordinated response. Not just the guard bees at the top frames, the bees 2 frames down, 3 frames down, bees with no line of sight to the opening, no way to have smelled the outside air yet, had already shifted posture, antennae raised, mid-task movements briefly stilled, and the beekeeper standing there saw bees getting agitated. She did not see what had just happened across the entire comb in the second before. A colony of between 30,000 and 60,000 individuals with no central nervous system ran a coordinated response in under 2 seconds, faster than the smell of open air could possibly have reached most of them, faster than light had fully entered the hive. Something reached them first. Something that does not behave like a chemical signal, does not diffuse through air, and does not slow down with distance inside a wooden box. Bee Mind. Subscribe, and the next one finds you automatically. If you have ever wondered what your bees are actually responding to in that first second, the standard answers. They smell you, they sense your fear, it's the smoke, turn out to be wrong. And the actual answer is the subject of this video. The strongest evidence is in the 3rd section, where the mechanism is named. Stay through to the end, because the last section changes what you reach for when you walk up to a hive. Every beekeeper learns the shift. You lift the lid, and the colony switches modes. There is a change in sound, a shift in pitch from the low working hum of a settled hive to something higher, more agitated. There is a change in the movement across the top bars. There is a sense, if you have opened enough hives, that the whole colony has registered something simultaneously. The shift feels instant, and the timing of it, when you look at it precisely, turns out to be exactly as fast as it feels. Pheromone molecules diffuse through air at a measurable rate. They spread outward from their source in a gradient, thinning as they go. In the first second after a lid is lifted, the scent of open air and human presence has not traveled more than 2 to 3 centimeters below the top frame. There are bees 2 full frames away, bees in the middle of capping a cell, bees carrying pollen, bees standing in a row along the midrib of a comb. That a chemical signal simply cannot have reached in that time, and yet those bees are part of the response. The behavior change documented in high-speed footage of hive openings happens in under 2 seconds, colony-wide. There is a fraction of a second moment before any visible alarm, a brief, coordinated pause across the comb surface, antennae up, bodies still, every bee stopping mid-task at the same instant. Too fast for pheromone, too coordinated for coincidence. Something else is the first signal. Now the second piece, which sharpens the first, starting with the answers most beekeepers carry, and why each one fails at exactly this point. 3 explanations come up when you ask a beekeeper what bees are responding to when the lid comes off. They smell you, they sense your fear or stress. It is the smoke. If you have ever wondered which of those is correct, the answer is that none of them accounts for the speed of the first response, and the actual mechanism is what this video is built around. Smell is a real input. It is not the first one. Your odor does reach the bees, and they do process it, but it arrives into an air column that diffuses slowly, and the documented colony-wide response at under 2 seconds outpaces it. The bees furthest from the opening cannot have smelled anything yet. The fear explanation is also real in a narrow sense. Bees do respond to compounds in human sweat associated with stress. Those compounds are detectable, but they face the same ceiling, diffusion time. And the initial response is documented at the moment the lid shifts. Before any hand is inside the box, before stress compound release from the beekeeper has had time to reach the frames. The smoke explanation is the most persistent, because smoke does work. A well-smoked hive is calmer than an unsmoked one, and that is documented. But smoke suppresses the alarm response. It does not prevent the trigger. Smoked hives still show the initial coordinated pause. The smoke affects what comes after. It does not stop the first signal. The strangest layer of all of this is the one with the evidence behind it, the mechanism that actually explains the speed, and that almost no introductory beekeeping resource has ever named. The first signal is not chemical. It travels through the comb. It is mechanical. When the hive tool presses into the propolis seal and the lid begins to shift, the vibration of that movement propagates through the wooden box, into the frames, through the wax of the comb, and into the legs of every bee standing on any surface connected to the hive body. Before any molecule has diffused, before the lid has moved far enough to let in significant light, the physical shock of the opening has already arrived at every bee in contact with the hive structure. That vibration is detected by an organ most beekeepers have never heard named. Inside each of a bee's 6 legs, at the joint between the tibia and the tarsus, is a cluster of mechanoreceptor cells called the subgenual organ. 6 legs, 6 organs, each one exquisitely sensitive to substrate-borne vibration, movement conducted through solid surfaces rather than air. These are the same organs a worker bee uses to stand on the comb and read the waggle dance. When a dancer performs, her abdomen vibrates against the comb surface, and the watching bees read the frequency, direction, and duration of that vibration through the soles of their feet. The subgenual organ is built for exactly this, detecting information in the material the bee is standing on. The Johnston's organ in the antennae handles a second channel, near-field air particle movement and low-frequency sound. The acoustic signature of a propolis seal cracking under a hive tool, the scrape of metal on wood, both fall within the frequency range that organ is tuned to detect. The sequence, timed. The vibration from the lid being lifted reaches every comb-standing bee in milliseconds, faster than pheromone diffusion by an order of magnitude. Those bees shift posture. Many begin vibrating their own bodies, propagating the alarm signal further through the comb as a wave rather than a broadcast. Light enters next, and bees near the opening orient visually toward the breach. The chemical alarm cascade follows as the third stage. 3 sensory channels, 1 trigger, 1 sequence. Vibration always first. Translate that out of the lab and into your hive. The bees at the bottom of the brood box knew you were there before the bees at the top had seen a single photon of light. The comb told them, not the air. The comb. That connects to something you can change about the way you open a hive. Because if vibration is the first signal, what you do with the hive tool in the first 3 seconds is the loudest communication you are sending. But to understand why the response is the shape it is, you need to know what the bees think is at the top of that hive. Honeybees evolved in cavities, hollow trees in forests, rock overhangs, cliff faces. In those environments for millions of years, the events that caused a cavity wall to vibrate, crack, and suddenly admit light were not beekeepers with intentions and gear. They were honey badgers in the African range, breaking into hollow trees for brood. Brown bears and black bears in the northern range, tearing at bark and deadwood, cavity walls failing under several 100 kilograms of force. The alarm protocol bees run when a hive is opened, the vibration detection, the light as breach trigger, the rapid colony-wide mobilization, was shaped by exactly those events, by cavity walls failing under something large, heavy, and hungry. The threat model the alarm system is calibrated to is not a person in a veil. It is a large animal breaching a hollow. You, pressing a hive tool into a propolis seal and lifting a lid, are presenting the colony's sensory systems with a stimulus package that is functionally indistinguishable from that bear at the tree. Substrate vibration from force applied to the cavity wall. Sudden light where no light should be. A large silhouette above the opening. Every input lines up with the predator profile the system was built to detect. Resist the metaphor here. The evidence describes something specific, and the specific version matters more than the poetic one. The bees do not think you are a bear. They do not think anything, but the cascade that activates on the sensory inputs you provide, vibration, light, silhouette, is the same one shaped over millions of years by bear-level predation events. It has no alternate pathway for beekeeper who means well. The inputs are the inputs. The response follows. This is why experienced beekeepers who move slowly and deliberately work calmer hives than beginners who move fast. Not because the bees have learned to trust them, but because slow movements produce lower amplitude substrate vibration, gentler light increase, and smaller rapid silhouette changes. The first stage trigger is weaker, so the response is proportionally smaller. The mechanism explains what repetition taught without naming it. Now the section that ties everything above into one experience. The hive opening you have done dozens of times. Read through the lens of what the bees are actually detecting. The hive tool is the first thing you press against the box. The scrape of the tool around the propolis seal, that sound and vibration, is the first signal the colony receives. Not your scent, not your presence, the tool. Before the lid has moved a millimeter, the vibration of that scrape has already traveled through every frame, through every comb surface, through the legs of every bee standing anywhere in the box. The first message you send is the one you send with metal on wood. Slow that scrape. Reduce the force. The first signal is quieter. The smoke you apply before opening does not prevent the vibration wave. That wave has already passed by the time you reach for the smoker. What smoke does is interrupt the third stage. It masks the chemical alarm receptors, slowing the pheromone cascade that follows the light and vibration stages. Apply smoke before the lid moves and give it time to work inside the top bars. It is buying you time at stage 3. Not stopping stage 1. Knowing which stage you are managing changes how you time it. The direction of your lid lift matters in a specific way. A lid lifted straight up creates a large, fast-moving silhouette directly over the opening, matching the visual profile of a large animal rearing over a cavity breach. Tilting the lid towards you as you lift it keeps your profile lower and the movement more lateral. The visual input to stage 2 is softer. If something about the way skilled beekeepers move at a hive has always felt intentional without ever being explained, it was. They learned the colony's sensory thresholds through years of feedback. You now know the mechanism those thresholds are built on. The hive tool is the loudest thing you bring. You bring it first. That is the variable most worth changing. I want to hear from you on 2 specifics. What the moment was that first made you feel the bees were reading you before you had done anything, and whether knowing this changes what you reach for first when you approach a hive. If you know a beekeeper who keeps asking why one hive is always difficult, send them this. The answer is probably in the first 3 seconds. That is the video. Comments open. Next one drops soon.